people at the back hear me? Yes. Good, thank you. Okay. So thanks, Sean, Stefano, and Dan for putting this together and for having us all here. So I was asked to say something about broadly the theme of the gravitational path integral. So I decided to talk about looking at black holes from very far away and very extremal. And this is work recently done with my student Ilya Rakic of Cipriani and Dalmarov, and the star of the show, Maciek Kozlowski, who basically did all the heavy lifting in the program. So I'm following on from Luca and Cynthia, who made my life easy by saying some of the things that I would have said naturally. So let me start with a slightly broader motivation, but I'll speed up through this since I don't have to say all these words again. So, if you look at non-supersymmetric black holes, especially extremal ones, there's a story that we can tell going back to what Stephen Hawking, that these black holes appear to have non-trivial degeneracy of states, non-trivial entropy at zero temperature. People in the classical relativity community were bothered by this because it seemed to violate the third law of thermodynamics. But that's not really a problem per se, because it's a classical computation, semi-classical computation. It doesn't say anything about quantum. But there's a serious problem that was pointed out almost 3.5 decades ago, namely that it poses this particular feature of the black holes having degeneracy at zero temperature, poses a challenge for how these black holes populate. So if we look at the deviation again from extremality, at small temperature thermodynamics, the energy scales quadratically naively away from extremality, but the entropy scales linearly. So if you're at low enough temperatures, then the black hole doesn't have enough energy to radiate even a single Hawking quantum, which makes it sort of problematic in terms of how the Hawking radiation process would go. We understand this, and I believe that there's an upcoming paper that will explain how the Hawking radiation process is modified by quantum correction by Mukund. Of course, various attempts have been made at address this puzzle. I've listed a couple of things that people talked about in the intervening decades. But the upshot, which I think is the right way to think about this problem, is that there is no macroscopic degeneracy at zero temperature. Black holes, as the central dogma would say, are just ordinary objects. They obey ordinary laws of thermodynamics. They have small, if degeneracy, if at all, at zero temperature. So this is something that came out of work of Henry with Joaquin and maybe 5-6 years ago, and then if you see more paper of Luca and Joaquin, who basically made it sharp in the context of non-supersymmetric. And what I will discuss today is a non-supersymmetric problem. So the point that they made was that the semi-classical analysis we have to do with some care. Usually what one does is we sort of find the dominant saddle, which is the extremal black hole, and then sort of look at the action and say that's a semi-classical entropy. There could be multiple saddles, but importantly, as you go to low temperatures, the one loop determinant around the saddle is important. And this is something that we've only appreciated in the last 5-6 years. So it was known that one loop corrections around black holes come from the near horizon region. This was worked out in the early days by, about 10 years ago, by Ashok Sen in the attempt to sort of understand black hole entropy from the attractor mechanism and entropy function analysis that Luca mentioned in his talk. But what was not done in those days was understand how this one loop determinant depends on the deviation from extremality. So what Sen computed was the leading logarithmic correction in the area of the black hole by looking at the one loop determinant, but Sen did not try to regulate the one loop determinant carefully enough to extract the correction, which is the prefactor to this exponential answer. Okay? And this contribution can be nicely isolated by asking what are the fluctuations in the near horizon region, and realizing that among those class of fluctuations, you not only have massive modes who accumulate to give you this log x naught correction, but also massless modes. Because they're gapless, their determinant a priori is not well defined. if you regulate them in a small temperature, then the regulated answer gives you a power law in temperature, not just an exponential correction to the extremal entry. So this is our current understanding, and one way to derive this answer is the fastest way, in my opinion, is to appeal to the fact that extremal black holes, all of them, have a near horizon throat, which is the radius 2 throat. And this throat basically says that even though you start with a black hole that has time translation of cubic symmetry, as you go to the near horizon, the time translation isometry gets enhanced in SL2. And once you have this SL2, you can either use this dimension reduction down to two-dimensional JT like gravity, and you can understand the quantum methods by looking at what are the gapless modes in this JT image. Alternately, you can basically sort of look at the fluctuation operator in the horizon geometry and realize that this fluctuation operator has a set of 0 modes. And if you sort of have black holes which are non-trivially fibered and walk over some base space, as will happen, for example, curved black holes, they are not radius 2 times some internal space, they're radius 2 fibered over a 2 sphere, then this picture of just dimensional reduction down to 2 dimensions is mildly suspect. So in that case, you probably just want to stay in the 4-dimensional near horizon geometry and study the 0 modes. And this was worked out a year ago by Ilya and Joaquin, and also by this paper from the Harvard. In all these discussions, whether you work in the 2-dimensional picture or in the full higher dimensional picture, the discussion almost always focuses on the near horizon, as Luca emphasized in his talk at the beginning. Once you identify the 0 modes in this throat, you then figure out how to compute the one-loop determinant by making the throat not infinitely long, but finitely, but making it finite but large by turning on a small temperature. But all these calculations nevertheless still only stays in the throat. It doesn't go out into the system. Okay, so the question I want to pose today and ask is a variant of that, which is, can we compute the quantum corrections to these black holes without referring to the near horizon? After all, we live in a 4-dimensional universe, let's say, and we have a right-dimensional black hole. I don't want to go to the near horizon region, I don't want to go into the radius 2 throat, look at 0 modes and ask what's happening. I want to be able to sit out far away and ask, could I have deduced from first principles that the features that I showed you before? Okay. The goal here is to make no explicit use of the radius 2 factor at all. And I want to emphasize that because the original calculation that was done by Luca and Joaquin did work in a full geometry. They sort of split the calculation into the near horizon and the far region and estimated both pieces separately and used the fact that the near horizon calculation was completely under control for computing the one-loop determinant. We don't want to do that. We don't want to have any kind of what I would call some kind of asymptotic split between the horizon and far region, and just give you one geometry and ask what is the one-loop. Likewise, since I'm going to be non-supersymmetric, I don't have the luxury of finding new saddles. So Luca basically explained how one might compute things in supersymmetric examples by staying far away. But here I want to sort of ask the same question to non-supersymmetric. And the one other thing I want to do is identify the analog of the near horizon modes, mode by mode explicitly. Because I want to say what is happening in the geometry that is responsible for these points. So I made two claims. So the first claim is the following, that the near horizon 0 modes, and I've been well studied in various examples of extremal black holes, they uplift to off-shell modes of the quadratic fluctuation operator around the black hole saddle. And in particular, these off-shell modes have eigenvalues which scale linearly with the Max-Born frequency. So if you're at low temperature, there always exists a family of modes whose eigenvalues are basically linear in temperature and with overtone number and linearly proportional to the overtone number. And they can arise from many different places. I showed you an answer which had a t to the 3 halves. That answer comes from a universal set of 0 modes that exist in the graviton sector for any extremal black hole, and that has been traditionally referred to as the Schwarzian mode, so I'll explain what that is. So you can think of it as the S-wave sector of gravity. It doesn't sort of depend on the structure of the internal space, it only depends on the radial and temporal coordinates. Then in addition can be other zero modes of associated with the background geometry. They could either come because your background geometry has additional isometries. It could have rotational isometries, it could be axisymmetric like Curry, in which case there is U1 isometry associated with rotations around that axis, or spherically symmetric like that in Nordstrom, in which case you have an SO3 rotation group in 4 dimensions. Or there could be gauge fields which are sourced in the solution, and those gauge fields also have symmetries. It could be abelian or non-abelian depending on what kind of black hole is there. Second, so I'll show you this in a class of examples. And second, I'll resolve a puzzle which bothered us for a while. So a year ago when we studied with the curved black hole, we basically were expecting to see 2 families of zero modes of curved black hole. One associated with the Schwarzian, which is related to sort of the universal ADS2 part, and another associated with the abelian isometry of rotations around the curved black hole, the axisymmetric solution. And we sort of tried finding those modes in the near horizon and the full geometry, in the full 4-dimensional near horizon geometry by picking a particular gauge choice, which is usually used in GR, the harmonic gauge. And we found that the mode that was conjectured to exist is singular in that gauge. I'll explain why that happened to be the case and why the harmonic gauge is a disaster for class of asymptotic for vacuum and sensors for this kind of problem. Okay, so this is the outline. So I'll first explain the class of modes analytically in an example that's easy to explain, and I can show you explicit formulas and show you how, as you go to the temperature, these modes get concentrated in the near horizon. That I'll do in the BTZ geometry. And then I'll show you just that we're not sort of fooling ourselves how to do this in other examples. I'll do them for Nordstrom ADS4 and show you where the contributions come. And then I'll briefly sort of clarify this bit about what happens about the Ricci flat geometries. But what I want to then spend some time on is highlight an issue with choices of ensembles. What is computed where, and how to actually do comparisons between near horizon and asymptotic calculations. Something that the experts appreciate, but it's not fully understood by most people. So I want to clarify that because that's important. And that will sort of lead me to the final discussion about whether the BTZ black hole has a rotational zero mode or not. Argue that it doesn't. Okay, so let's start with BTZ geometry. So I'm going to start with just, so in each case I have to tell you a context of where I'm computing and what I'm computing with. So I'll just start with Einstein-Hilbert action with negative cosmological constant in 3 dimensions, no matter, and there's a solution to this which is the BTZ solution, and I'm going to Euclidean something I'm going to try to compute 1 meter. So the right boundary condition to impose here is to fix asymptotic values of the boundary condition at infinity in radius 3. So I'll fix the boundary condition that corresponds to the thermal circle period and a rotational chemical potential and angular velocity for rotations along the spatial circle of the BTC. Okay. So if you are a ADS CFT person and you are asking what are you doing from this dual CFT, I'm going to try to compute a grand canonical partition function where I have fixed temperature and chemical potential for rotation. So what I'm fixing is T and omega, which are related to the parameters R plus and R minus for the solution. And the near extremal limit, I can sort of say by taking the linear combinations of T and omega into left and right temperatures and taking the left temperature to be much smaller than the right temperature. Good. So we take the solution and we perturb it. We'll sort of look at linearized perturbations. And if you are like me and thought about this for a while, you would have said, sorry, what am I doing? Because this is 3D gravity. If I actually want physical graviton modes, there aren't any because they're all localized to the bound. That is true, and it's true in the sense that the only physical graviton modes can be always pushed back by a choice of gauge to the boundary, but I can always choose to work at some random gauge and make them manifest in the physical space. Okay. So I'll just pick a random gauge. So in particular in this case, I'll just pick the harmonic gauge. And then write down the fluctuation operator with this harmonic gauge fixing. So once I pick a particular gauge, I also have to worry about what the Fourier-Popov determinant of the ghost do, and I've just written down the ghost action in this context, which is basically the Laplacian minus Ricci acting on work force. Okay, so if I look at the fluctuation operator acting on spin 2 fields, the spin 2 part of the fluctuations, that is basically given by the so-called Lipnowitz operator, spin 2 Lipnowitz operator, which has this complicated expression, except that this is ADS DTC and ADS 3. So it's a maximally symmetric spacetime, so all of these things collapse, and you basically get Laplacian plus some mass. Okay. So if I go to the horizon, I get a geometry which is ADS2 fibered over a circle fibration over ADS2. And in that near horizon calculation, you will find a set of zero modes, which are basically the Schwarzschild zero modes associated with this ADS2 factor. Okay, I won't write down the explicit expression, I'm just going to show you some of this. So this is work out in places in the literature. So those modes happen to be in the kernel of this Lipnowitz operator in the near horizon. So in other words, if you take the spin 2 operator and go to the near horizon region, there exists a set of modes that are annihilated by the Lipnowitz operator and are completely localized in the near horizon, because the near horizon throw decouples from the asymptotic. The question is for us, what do these such modes correspond to in the full space? So I just want to ask, are there eigenmodes of the spin 2 operator which exist in the full space-time, and once I take the near horizon decoupling limit, descend completely down the road. Okay. So the eigenvalue problem actually turned out to be very easy to solve analytically, and in fact we did some hard work, but it was mostly done in these earlier papers by Dan David and Kasper Keeler and Zerchowski. So if you basically look at spin 2 fluctuations, here is a full a set of eigenfunctions of the spin 2 operator. And you see the eigenvalues are this is the explicit eigenvalue for any left and right temperatures. But as the temperature goes, as the left temperature gets very small, as T left goes to 0, these eigenvalues basically start being linearly proportional to T left. Okay. And N is basically the Matsubara move down.
I still don't know what you mean by T left and T right.
T left and T right. So we are in two dimensions. So we have a temperature and angular velocity. Right? And the theory has local conformal invariance. So I can basically look at a frame where I move either right along the light path or left along the light path, and I will see T left and T right for those observers. Thanks. Good. So the temporal dependence of these eigenmodes is basically e to the I omega n t, where omega n is basically the Matsubara frequency, and the Matsubara frequency at small frequency is basically small temperature is T. These modes have some radial profile that is completely elementary, but I'm not going to write those modes down. And I should say that this was also discussed in also a recent paper by Capes, Albert Locke, and Kira Cole. What instead I want to do is show you what these modes look like as I approach extremality. So I just take the eigenmodes and look at the norm with respect to the appropriate inner product on the space of fluctuations. And I'm plotting it as a function of proper distance from the horizon. So as temperature goes to 0, you see the norm. So at some higher temperature, there's a norm which sort of is concentrated in some fashion and it dies off as you go far away. But as temperature gets smaller and smaller, the norm concentrates closer and closer towards the horizon. The eigenvalues go to 0. In particular, exactly when T left equals 0, I have a set of 0 modes, because then these eigenvalues are all 0 eigenvalues, 0 eigenvalue modes of the Lipnowitz operator. But more importantly, the concentration, the sort of support of these modes descends closer and closer to the horizon. Okay? So in some sense, these are really the analog of the Schwarzschild modes in the full geometry. because they are the ones that, if I sort of put the decoupling limit, I would basically throw away the entire probability except the region close to the horizon, and I would just see the zero modes localized in the near horizon.
Okay, if you would use some coordinates where the probability is from the horizon, then you say where this peak is located?
The peak sort of keeps gets close, so you have to decide how you're going to sort of measure in some gauging gradient fashion where the
Probability is from the horizon.
so proper distance to the horizon, the peak goes arbitrarily close to the horizon as the temperature goes. And there's something more you can say, which is I haven't shown you the wave function, but if you look at our paper, the wave functions are explicitly given, and you'll see the wave functions actually descend to the Schwartzian wave functions as you go towards 0. So I can emphasize this, I want to say this now. So the modes exist for every value of Matsubara frequency except 0, the constant mode, and modes with frequency plus minus 1 in Matsubara units. Okay. Those modes are not normalizable and they are therefore not part of it. So this is exactly what you expect from the Schwartzian analysis. You expect that you have all but 3 modes associated with the fluctuations in the near horizon. Okay. So let's see what this means. So I just convinced you that, told you that we found a class of modes that have linearly scaling eigenvalues with temperature. And if I now compute the one loop determinant, ignoring every other fluctuation mode, but just the contribution from these guys, I would get, after theta function regularization, I would get a factor of 3/2 log t in the log of the one loop partition. Therefore, the one loop partition function will scale as a power law in temperature with the power set by frequency. And this is good. And not only is this good, in this particular example, it turns out that these are the only set of eigenfunctions of the spin-2 ignorance operator with such low eigenvalues. This you can prove because the problem is simple enough that you can show exactly. So, and I'll come back to this point, but let me emphasize something now. The BTZ geometry, the solution I wrote down, whether it's a low temperature or arbitrary temperature, it has a killing isometry associated with angular rotations, d by d phi. My previous argument would have suggested that there is a 0 mode associated with those angular rotations. Claim it doesn't exist. The answer that it doesn't exist is consistent with the field theory calculation I'm going to tell you in a second. I'm going to postpone why it doesn't exist to the end of the talk. So just to emphasize that this 3/2 power is the right answer, let me remind you of the calculation which started this discussion. It was the calculation of Ghosh, Maxwell, and Togashi, who basically took estimated the BTC partition, the near extremal BTC partition function by starting with the boundary calculation. You assume that you have a boundary CFT dual to this BTC geometry with a vacuum, isolated vacuum and a twist gap. And then you work out a one loop partition function and you get 2 pieces, one which is some shift of the extremal energy which is not necessary for our discussion, but you get a piece of the one loop partition function which is 3/2. And I emphasize that you get 3/2 log t, whether you work in an ensemble with fixed temperature and fixed angular momentum, i.e. the canonical ensemble, or you work in an ensemble with fixed temperature and fixed angular velocity, i.e. the grand canonical. And we'll see why these modes. So absence of these modes is consistent with this answer, but I haven't explained why they don't exist in the new horizon. So this was nice. So BDZ was nice, but sort of an easy example. Let's try to do something slightly non-trivial. And you'll see why it's somewhat less easy than the BDZ. So again, I'll start with the simplest possible theory for which I have an extremal black hole, namely Einstein-Maxwell with a negative cosmological constant. And there's some boundary terms which are not important for this discussion. I chose Einstein-Maxwell with a negative cosmological constant simply to regulate my asymptotic boundary conditions. I'll say something about flat space or as I go. Okay? So they're electrically spherical charged four-dimensional Reynolds black holes, which are spherically symmetric, and in areas, here are the solutions. If you take L areas to 0 in an appropriate sense, you will get back a flat solution. Okay. Now, if you do the near horizon analysis, which was done in this paper I mentioned by Luke and Mukund, you'll find three families of zero modes. One, which is the modes associated with gravitons, associated with the near horizon areas 2 region, which I'll still call the Schwartzian modes. So you can think of these in the near horizon as the modes associated with large diffeomorphisms of the areas 2. There is a second set of zero modes associated with the gauge field that exists in this background, which source in this background. I can do gauge transformations which don't die out of the boundary of this areas 2 probe. And they will give me a set of U1 zero modes. And third, the solution has an SO3 isometry associated with rotations of the 2 sphere, and so I should expect killing set of zero modes associated with this killing symmetry associated with these rotations. Okay? So we find all three of them, and then I'll explain how each of them contributes and which ensemble each of them contributes. So you might say, okay, fine, this is a problem that you can write down the quadratic fluctuation operator, compute its eigenspectrum. Easier said than done for reasons that are slightly complicated. No one actually has done this calculation in this literature for the following reason. You need to do some bit of groundwork. The first reason is that it's Einstein-Maxwell, and both Einstein graviton and the background has non-trivial gauge fields turned on. So we need to quadratic fluctuations, the physical graviton fluctuations will mix with the photon fluctuations. If you are trying to study the problem at the level of on-shell modes, then you can simplify your life by trying to find some gauge in which you can actually decouple the photons and gravitons. So that's technically not a problem, but in general, you have to worry about how to actually decouple the spin 1 fluctuation from the spin 2 fluctuation. Second, a slightly more serious problem is that I want to compute the one-loop determinant, and I want to study the Euclidean action. But the Euclidean action famously is not sign definite in gravity. In Einstein-Hilbert theory, there's a prescription, the prescription that goes back to Gibbons, Hawking, and Perry from the 70s, and their argument was the mode that's not signed, causes this sign indefiniteness of the Euclidean Einstein-Hilbert action is the conformal mode. So by going to some kind of transverse traceless gauge, you can sort of pick, you can decouple the conformal mode from the rest of the physical fluctuations and integrate over the conformal mode separately. And by picking a suitable contour of integration for the conformal mode, you can cure the problem and you can sort of isolate it completely from the physical fluctuations. The conformal mode doesn't talk to the class of transverse traceless gravitational polarization, physical polarization. But for Einstein and Maxwell, this is not an option. Spin 1 part couples to spin 2 parts, so there is no easy decoupling of the conformal mode to pick some simple gauge. Okay. So, as far as I know, nobody's actually, we do agree to this, and nobody's actually asked how to regulate the Einstein-Hilbert Maxwell action to figure out a contour prescription. And there was some recent work by Barov, Santos, and Liu in the last couple of years. So inspired by their work, Maciej came up with a nice prescription, which was to basically integrate the Maxwell field along the purely imaginary range. So we can modify this prescription, but for now I'm just going to take this and run it.
The Euclidean Maxwell field?
The Euclidean Maxwell field is the imaginary range. Which means something about what the Lorentzian section is. You have to so I also need to ensure that the fluctuations, the modes I pick are physical. If the modes are not, if I sort of end up with unphysical modes, I actually have to worry about the ghost determinant as well. Okay. So my gauge fixing, whatever I do here to pick and then do the contour of integration, I also have to supplement it with some gauge fixing terms. I better find modes of the quadratic fluctuation operator in the physical channel. Otherwise, the answer is somewhere in having to deal with the ghost as well. Okay. So we're going to try to find this with the right gauge choice. So again, for that reason, it turned out in this problem not to look at Raman gauge, but with some kind of modified gauge choice which mixes the harmonic gauge condition with some background Maxwell condition. So this is a particularly reasonable gauge to pick. So with this gauge choice and Lorentz gauge choice for the gauge field, you can count the number of gauge conditions is what you would usually impose for transverse traceless gravitons, let's say. And now we can sort of start with this gauge choice, stick this gauge fixing functional into our action, work out the quadratic fluctuation operator, diagonalize it. But that problem now is, once you pick the gauge fixing and you've done this exercise, the diagonalization is easy because you get both symmetric sector by symmetric sector. And the three modes I talked about are in different symmetric sectors. These are spin 2 fields from the radial and temporal direction point of view. These are pure gauge modes, and these are scalars from the point of view of the temporal and radial points.
Why did you write down the last time the first gauge choice? That is 0. Do you have
It is 0 when I impose Lorentz gauge,
Yes.
but if I didn't want to impose Lorentz gauge, I could keep that. So it's true that in this gauge choice it's completely 0. So for fluctuations which, for example, be fully decoupled, it might not be useful to just keep it as a regulator cost. Okay, and of course, this was all done numerically, so I'm just going to show you some results. And I apologize, the plots look very boring, but they're pretty impressive. You should think about them. And my director of works, I'm going to show you a couple of those. So there's a quadratic fluctuation operator we're going to call D. And again, I just want to illustrate two facts. This quadratic fluctuation operator in different symmetry sectors has eigenvalues which scale linearly with temperature and one's bar of mode number. So the eigenvalues are n times t. For the Schwarzschild modes, again, n equals 0 and plus minus 1 are missing. And we see that over many decades, the eigenvalues scale linearly in temperature. I'm plotting the eigenvalue as a function of rescale dimensionless temperature. And the plot is, so this is for very low temperatures, and I sort of zoomed out and showed you for one more decade just to show you that it sort of extends further. Yes, Luca.
What is alpha?
Alpha is some numerical constant. It's not relevant because it will drop out of the predominant calculation. So there's some overall normalization over that eigenvalue.
But T is dimensional.
T is dimensional, so
So I'm just wondering whether alpha indeed correctly scales like the breakdown scale.
yes, it does. So that's a short answer. I didn't write it there. I should have probably written the eigenvalue as T over TQ, and then alpha will be appropriate dimension.
So alpha doesn't depend on n or t.
Alpha in particular doesn't depend on n or t. That was important. Yes. So the n and t dependence is explicit. Alpha is some background dependent parameter. I have written it because if I look at right, if I took out the dimensions, then alpha would have been some order 1 number. The last plot is basically showing you that this just shows you that these two plots show you that the eigenvalues are linear in temperature, but I also want to show you that there's linear dependence in n, the mode number. So this is just a collapse plot that I just rescaled the eigenvalues by n and plotted them, and they just lie on top of each other. So it's clear the eigenvalues scale linearly. That was a Schwarzschild. Now I just keep scrolling because it looks similar, but they're different. They're really different plots. This is the U1 gauge mode, and now you miss the n equals 0. Okay. And same story. And if you do the rotational modes, there's an SO3 family. I just pick the n equals 0 as you miss a quantum number, and again you see precisely the linear field results. So, and it's more interesting to ask the same kind of question we asked before, which is how do these modes behave as you go to the near horizon regions. So if you look at the norm as a function of proper distance, if you correctly normalize the norm so that the integrated norm is 1, then you see that the concentration is very close to the. Here, this numeric started very quickly for us to imagine who did all the work to get to very low temperatures, but you see that there is a descending growth. So, and I just showed you one of them, but the story is similar for the Schwarzschild and the U1. So let's now take stock. So we have these three families, and let's just try to compute the one loop determinant from these three families. By being completely agnostic and just say we have this mode. So if we compute the one loop determinant, the Schwartzian mode, as I did in the VDC case, it gives us a factor of 3 half log. Okay, because there were modes n equals 0 plus minus 1 are missing, and that's why you get 3 half log. The rotational zero mode misses n equals 0, so you get half log t, which is the right answer. The rotation mode, sorry, the U1 mode gives you half log t. The rotation mode gives you half log t per axis of rotation, but there are 3 axes, it's an SO3 gauge field, so that's the extra factor. So now this is the correct answer around a single saddle, namely the Rice-Nordstrom solution. What we're doing is fixing asymptotically the temperature, the chemical potential for U1 charge, and the chemical potential for rotation. Those are the boundary conditions in asymptotically flat space that are correctly non-normalizable. So you sort of fix your size of the circle at infinity, and as you go around the thermal circle, you ask for the gauge field to come back to pick up a holonomy which is proportional to a chemical potential, and you ask for the rotation modes to come back to themselves upper angular velocity. You cannot, in flat space, fix asymptotically the values of charges, because charges fall off like 1 over r to some power, there's a Newtonian fall off, and that is definitely normalizable. So there's no meaningful boundary condition which fixes charges in asymptotically flat space. Okay. So any calculation of the gravitational path in asymptotically flat space-time, or in general in asymptotically ADS space-times, in general dimensions, only works in the grand canonical. There are exceptions to this statement, which I can talk about afterwards, but they have to do with ADS boundary conditions in low dimensions. But I have only computed the partial function, the answer with fixed chemical potentials. But as Luca emphasized, once you fix chemical potential, I can do 2 pi I shifts to beta times chemical potential, and that does not change the partial function. So if I keep the minus beta mu, 2 pi I shifts of the minus beta mu doesn't do anything. So it's not sufficient to find the answer around one saddle. We actually have to sum over all integer shifts of these chemical potentials. So if you want the grand canonical answer, this will be the contribution from around for the one loop determinant around one saddle. Then you're supposed to get the contribution from all other saddles which are related by integer shifts of the chemical potential, and then sum them up. Having done so, you Legendre transform to the canonical ensemble and figure out the answer at fixed charges. Yes?
Could you assuming that the charges are integers?
I'm assuming the charges are integers. Yes, I'm assuming that there is an underlying data quantization condition and charges are integers, so I'm allowed to do the question. It's of course easy for the angular one. Okay, so let's turn the page, and so that's all I have to say about Rice-Nordstrom. I don't have a general answer for the saddles. All I wanted to illustrate was there exist modes which we could have figured out in the full space time, which would have shown us the contribution of the nearest answer. Okay, let's talk a little bit about zero modes of rotation. So, if you look at curve, extremal curve, you expect that curve breaks SO3 rotations into just U1. So you expect there should be in some SO3 family of zero modes for rotation. You should expect one rotational zero mode, which is a U1 zero mode. And as I said, we didn't find a mode. We actually explicitly argued and demonstrated that such a mode would not be smooth in harmonic, would not be smooth poles of the curved black holes for us. But later on, multi-data calculation for curve ADS4 and curve Newman, and there was no problem. We managed to find the zero mode in these two examples. And the reason, which I'll now explain, has to do with the failure of the harmonic gauge condition for curve black. So the harmonic gauge fixing functional is basically this. If you are in transverse traces gauge, you basically take a trace removed per fluctuation and take a divergence. If you have a zero mode, And if the new horizon is generated by diffeomorphism, then the fluctuation is basically pure diffeo. And if you sort of work out what it is for the Schwarzschild mode, you can start write down the pure diffeo. What you expect for the rotational modes is a diffeo along the angular direction. So you can figure the angular killing field, and you can sort of dress it up with some temporal and radial piece to figure out what it must satisfy to be a good case for the zero. And this was a case that comes out by doing some ADS2 analysis that was done by Sen long time ago, pretty much by composition. Okay. So this looks like a potential rotational zero mode for curve. If you then go and evaluate the gauge fixing condition, it doesn't satisfy the gauge fixing. It doesn't satisfy this harmonic gauge fixing condition. So this functional GF mu evaluated on this perturbation H mu generated by psi is not zero. That's okay. No one said that you have to find a story that just works on the nose. You can always fix out something that's not in a particular gauge by doing a diffeo, doing a secondary diffeo. Except this can't be a large diffeo, it has to be a small diffeo. So let's say in addition to the H mu generated by psi, I have another vector field zeta, which is a small diffeo, which brings me back to harmonic gauge. Okay. It's not hard to check that zeta has to satisfy an inhomogeneous second order equation, which is of this form. So this demanding that nabla psi symmetrized plus nabla zeta symmetrized is harmonic in harmonic gauge using this condition. So GF is now just evaluated from the psi part. If this gauge condition can't be imposed, or if the gauge condition of the problem, it can be the signal of it is that the operator that appears on the left hand side is an elliptic operator, nabla squared plus VG tensor, has a kernel. Okay. If it has a non-zero kernel, it means you can't invert this operator, in which case you can't sort of find a solution to the homogeneous equation. For Ricci flat backgrounds, R mu is zero. So this operator is basically just Laplace acting on conforms. It's very easy to show that there is a zero mode for conforms in any Ricci flat background, because there's a zero mode for gauge fields, which is whose fluctuation operator is Laplace. So basically, starting with a scalar Laplacian, you can actually construct a psi, a zeta, and then show that this is the kernel of this operator for curve. The other way to say it is if you fix the harmonic gauge, you won't find a zero mode in the physical lattice fluctuations, but you will find a zero mode in the ghost kinetic. And just to emphasize that, let me point out something that I glossed over before. If you stare at the Fourier-Popov determinant, the ghost action is the very same operator that appears in the ghost kinetic. So the failure can be deduced by either asking whether your gauge condition fails, or by asking whether you have physical ghost modes that are contributing. So we haven't done the calculation of the full curve geometries, but I think we should be able to see this issue in full near extremal curve. And I should say this is not a problem for curve, it's just a problem for any Ricci class or rating class for background. If you try to find quadratic fluctuation operator, harmonic gauge is a disastrous gauge to use. Okay, I have 5 minutes, so let me say something about ensemble choices. So I already said that when I am in full space-time geometry, the right boundary condition to use is the grand canonical boundary condition, fixed chemical potentials. And this is what I said in words, that a symptotic to the gauge field goes like a constant, which is the chemical potential, plus a 1 over R power law follow, and you're not allowed to fix the power law follow because this guy is not more normal in sufficient high number of dimensions. There are exceptions in d equals 3 and d equals 4 in areas. However, in ADS2, if you're in the horizon region, the asymptotic solution in the ADS2 throat is constant plus linear. In which case, you're not allowed to fix the constant, you have to fix the linear term. So the right boundary condition in ADS2 is to fix charges and not the chemical rotation. So if you want to compare an asymptotic full geometry calculation with a near horizon calculation, you are going to have to figure out how to do the saddle sum and the Laplace transform before you do the comparison. Because otherwise you're comparing apples to oranges. All the discussion that I know of for the contribution to the power law in the canonical ensemble is worked out in the horizon region. And the claim is that having done so, having gone through the sum over saddles and the Legendre transform, the only contribution to the low temperature thermodynamic entropy is due to the 3/2 of the Schwarzian. The rotational and the hitting isometric zero modes do not contribute in the canonical ensemble. I am not making a statement on the canonical ensemble because as far as I know, nobody's discussed that very carefully in general examples. Okay, so I have a couple more minutes, so let me quickly wrap up with BDC. So let's just go back to the BDC case, and here is the near horizon geometry of BDC. So the circle fibrillation over ADS2, explicitly written down here. The one form in ADS2 is one is SL doing very one. You can try to find a zero mode associated with this angular isometry, and in the near horizon. Okay. So I just went through the exercise for curve. So you just take the same thing, make some changes, one dimension lower, no angle dependence, much easier example, you find it. But you have a problem of plenty of zero modes. I already told you the Schwarzian zero mode give you all the t to the 3/2. In fact, if addition have a rotational zero mode, then I get an extra factor t to the 1/2 in the canonical ensemble. Which is not the right answer for the CFT. So I said the CFT answer is t to the 3/2, whether you're in the canonical or grand canonical ensemble. But there's a more fun piece to it. This mode doesn't seem to extend to the full space time. So what's going on? So this is basically a slightly involved calculation of the same thing that I was telling you before. Why you get t to the 3/2 in both the canonical and grand canonical ensembles from a dual CFT computation. So basically paraphrasing what George McMillan did. Okay. So I said the modes there are zero modes, but we never said what scale, which was a question that Luca asked, this gap scale at which they contribute. So I assume, without saying so explicitly, that whenever I have a zero mode, I can always regulate the solution by turning on a small temperature, and the zero mode gets an action scaling like linear in temperature with some scale set by this quantum scale, gap scale. Again, if you work out generally in terms of extremal black hole thermodynamic data, what this gap scale should be. And for the Schwarzian mode, the gap scale is set by the specific heat at extremal. It's basically the derivative of entropy with respect to temperature at fixed charges with some factors. But for rotation and killing and for gauge fields, it's set by the appropriate angular or charge susceptibilities, which is basically the variation, rate of change of the extensive parameter with respect to the intensive parameter. A mode will contribute only if the susceptibility is finite. If the susceptibility diverges, the mode doesn't contribute. A BDC black hole, this solution in the extremal limit is rotating at the speed of light. So the angular velocity is 1, independent of its angular momentum. Therefore, its susceptibility diverges. This is consistent with the mode that exists in the near horizon having no uplift to the entire spacetime. And this is one example where had you done the calculation in just the near horizon region, you would have gotten the wrong answer without knowing the CFD anchor, because you would have said, I have two families of zero modes. But one of them exists, but does not contribute because it cannot be regulated. It doesn't contribute, it just decouples from the vector. So putting that together, you get this t to the 3 halves. And in fact, you get the correct answer, including the log S0 correction without including the rotation of 0. So that's the story for BTC for which we have to anchor. But I want to say something nice, which is something non-trivial for which we don't have a proof, we have to have a evidence, and I won't show you a plot. You can ask what happens in Rice-Nordstrom in flat space. In flat space Rice-Nordstrom, the chemical potential for charge also goes to constant independent of charge as you take go to external. Okay. That means the U1 gauge 0 mode should not contribute to extremal Rice-Nordstrom thermodynamics. Okay. We verified this by, when I wrote this, I said, checking this, but we actually verified this, that the mode doesn't exist, it gets out of the spectrum. Okay, I am out of time, I believe, but here are my summary. So I basically told you some story about how we might identify the modes that have been studied in the last 5-6 years in the near horizon geometry, in the full space-time, and how they correctly reproduce the thermodynamics of how expected thermodynamics of their extremal black holes. There are other things one can say about how these results are robust to finite straight scale corrections, and I'll just mention here something that some people have been thinking about, including myself, which is it's nice that we can sort of complete this one loop determinant around using the Euclidean techniques, but what would be really nice is if there is a story that could be told directly in your energy. Are there physical modes that contribute to these, which we can identify as being responsible for these corrections? And it's a very beautiful formula from about 15 years ago by Derek Hartman, which tries to do the one-loop determinant in terms of for the normal modes. There's been some attempt to understand, use that for the case of EDC, but as far as I know, the general story is yet to be. That, let me stop and take questions.
What happens if you extend this to supergravity?
So in supergravity, the story would basically have, you would have these kind of modes. So now the question will depend whether you have supersymmetric solutions to supergravity or non-supersymmetric solutions to supergravity. So let's say we took Rice-Nordstrom. Instead of Einstein and Maxwell, I made it Einstein and Maxwell in n equals 1 or n equals 2 supergravity in 4 dimensions. I would in addition have presumably, so if the solution was not supersymmetric, I would say that you won't have gravity no zero modes. You only have zero mode associated with the gauge field and metric. But if the solution was supersymmetric, you additionally have gravity no zero modes. Because the background preserves supersymmetry, so there are zero modes associated with gravity.
Would you still have the results be consistent with next?
Yes. So this one can check in yes. Short answer is yes. The reason is that you see these calculations are one loop around a fixed background. They don't. You can ask whether that calculation is robust to including alpha prime corrections. And that statement is yes, because you're not asking about Planck scale. Okay, you're only asking one loop in Planck scale, but that you can ask around any fixed background at any alpha prime. And the example we worked out was the ADSA example, which basically is the verification kind of thing that can be working and equal.
Can you explain a bit what are fix the charts? I mean, I can rebuild the charts by Gauss.
Question is, what are the boundary conditions of pathing? So it's not a question of using Gauss or read out the chart. The question is, what boundary conditions you want to use for pathing? So the way I think about how you write down the boundary conditions for pathing, is you fix modes that are not normalizable and determine modes that are normalizable. So let's look at this example. Let's say we are in D equals parts in. So if I look at a gauge field in ADS, actually this answer doesn't care, it's the same thing. In flat case, we go faster. The gauge field basically has a constant mode. Let's say we're in radial gauge. So I fix AR 0, an angular component. And then there'll be another fix in the linearized equation which basically goes like 1 over R. Now, we can try to use the canonical time border line now for the Maxwell field and try to ask which of these two modes is normalizable. And clearly, this guy is not normalizable because that's fixing some asymptotic value and that will have some non-zero consequence. But this guy falls off fast enough that when you put in the factors of the measure, that integrates to its integral. So, fixing this guy means, since we are solving the second order equation, means that this guy is undetermined. So then if you look for any functional action or any functional value once you fix the Q, that will be divergent because I'm not allowed to add boundary terms in terms of this guy. So if you think in canonical language, you either get to fix canonical momentum or canonical position or some linear combination thereof. But the linear combination is only allowed when both the boundary conditions are allowed. So you either get to pick Dirichlet or Neumann, and in high enough dimensions, Neumann becomes an option. So a slightly more conceptually easy way to say is that if you think of scalar fields in ADS, which you probably know, near the right along the treatment bound, you are allowed to impose either Dirichlet or Neumann boundary condition, and that changes whether the conformal dimension is delta plus or delta minus. But once you're away from the one unit away from the right along the treatment bound, you're not allowed to impose Neumann boundary condition because delta minus goes negative, you violate unitarity bound of theory. But in the classical gravity, if you didn't know any ADS CFT, what you would realize is that that mode is not normalizable. There is no phase space with that solution. So this is very nicely discussed in this paper. Yes, sir.
So I should be able to tell from your formulas, but there's this like simple formula, I guess I learned from the paper, in other words, that if you have like a classical action that scales as lambda, then like the one piece scales as like lambda to C minus G, where C is the classical moduli space and G is like the dimension of the gauge roughly.
Yeah.
These answers, is it really consistent with that? Is it like automatic or? It's a little subtle to interpret that formula, that's why I asked. It's not,
I mean,
just count, you know, it's a little subtle, so it's sort of.
I'll give you a mnemonic which works in this case.
Okay.
For the short term, you can explain the t to the 3 half of the following. Each bosonic zero mode gives you t to the half.
Yeah.
Right? And if the spectrum was complete, all modes are there, zeta function regularization will give you a finite answer.
Right.
Right? But 3 modes are missing.
Yeah.
That's the 3.
Yeah, when you have these other examples, like when you fix M and J, you have like any channel of 3 has 1, like all those consistent.
Same argument, same argument because they're n equals 0.
Yeah.
So same argument.
Thank you again.